This is lesson 2 for grade 12 essential probability units. And we are looking at the difference between theoretical and experimental probability. It's pretty much what the words mean. A theoretical probability is a ratio that compares the number of possible successful outcomes to the number of possible outcomes altogether. And again, this is determined by calculation, or the blank is they're looking for the word, my pen's not working, they're looking for the word formula. Determined by formula or calculation. If you go back into lesson 1 real quick, theoretical probability is basically this formula, which I like to call desired over, this word I realized is supposed to actually be possible. I don't remember if I fixed that yesterday on the video. So desired over possible, it's a formula. If I were, remember this cartoon from 2 days ago? If I were Calvin, I would expect by theoretical probability that this strategy on my true-false test should give me a mark of 50%. That's what I expect. That is theoretical probability. Now, is that what happened? Not necessarily, because what happens in the real world when you try stuff is called experimental probability. It's a ratio that compares the number of times an event occurs to the total number of trials or tests, and it's determined by experiment. So I would get a true-false test together, get a class full of 30 Calvins, and say, you are not supposed to try on this test. You're supposed to flip a coin for every question. Heads, it's false. Tails, it's true. And then I'd mark the test at the end, and if I got an average in the class of 50%, then that'd be me saying, yeah, that's my theoretical probability, 50%. Or sorry, my experimental probability would be 50%. Notice the very big difference between the two. For an experimental probability, you actually have to do stuff. You don't just sit there and think about it and run a few numbers by. You actually have to run some sort of an experiment or get some data. Experimental probabilities can also be based on data. You've actually measured and counted stuff. Example 1. In a bowl, there are 4 oranges, 3 apples, and 6 bananas. Christina picks a piece of fruit at random. What is the chance that the fruit is an orange? Well, let's see. Desired over possible. I'm going to say probability of orange. That's the symbol that says I'm calculating the probability that the thing I pick is an orange. Well, desired over possible. There are 4 oranges, and there is 4 plus 3 plus 6, which is 13 fruits in the bowl. I'll just leave it as a fraction. So my probability is 4/13. What is the probability of Christina picking a banana? P banana. Well, there's 6 bananas. There's 13 pieces of fruit in the bowl. What type of probability is this? Is it experimental or theoretical? This was theoretical probability. Nobody actually picked fruit out of a bowl. Right? If I were to, again, take the bowl and say, all right, reach in without looking, and I guess you'd have to use some sort of claw machine or something, because I think the average person, even without looking, can tell the feel difference between an orange and a banana, unless they're, really, really not familiar with fruit. So they pick, and it's like, oh, it's a banana, put it back. Pick again, oh, it's an orange, put it back. Pick again, oh, it's a banana, put it back. So if I did that 100 times, and I got the banana 10 times, I'd say I got 10% for an experimental probability. Experimental means you actually did something. Look at example 2. Of the last 35 people to walk into a grocery store, the last 20 were wearing mitts. What is the experimental probability that the next person to walk into the store is wearing mitts? Give your answer as a fraction, decimal, percent. Okay, this time it wants all three numbers. So, desired over possible, or sorry, new formula. It's event occurs out of total number of trials. So my probability this time, probability of mitts, the probability of a mitted person is, again, the total number of successful events over the total number of trials. So here's my history. 35 people walked into the store. 20 of them were wearing mitts. So there's my fraction. Am I going to get a full mark for that? No. What do you notice goes into those two numbers? 5. So divide top and bottom by 5, you get 4/7. That would get you the full mark. And again, if your times tables are kind of weak, your calculator will simplify fractions for you. You just have to use your fraction button. Okay? So there's the fraction. The decimal, I should know this decimal. I got to write it out first. 1,42857. Whoa, that's, my pen went insane. 1,42857 to 857. So there's 1/7, 1/7, 2/7, 3/7, 4/7. So that's 0.571428 repeating. So there's the decimal. I guess you could round that somewhere if you wanted. And the percent, I'm definitely going to round it, is 57.1%. I'll round it to one place. There we go. So there's my answers as fractions, decimals, percents. Fraction, decimal, percent. Okay, so that's example 2, the grocery store. Example 3. Adam and Blake are playing snakes and ladders. They record the games and who won. Game 1 went to Adam. Game 2, Blake. Game 3, Blake. Game 4, Adam. Game 5, Adam. Game 6, Blake. Game 7, Blake. Game 8, Blake. What is the experimental probability that Adam won? Well, probability of Adam winning experimentally is we played 8 games and Adam won 1, 2, 3 of them. So 3 out of 8. Notice this time it doesn't say, give me a fraction and a percent. If it doesn't tell me, I'll do whatever I want, and I want fractions. Fractions just to me make the most sense. You can see the ratio, 3 out of 8. Decimals and percents I got to think about. I like fractions. I think most people who do probability, especially for a living, your statisticians and stuff, percents and decimals they would only use when they're presenting to their bosses. When they're doing their own work, it's probably fractions. What's the theoretical probability of Adam winning? Now, anybody want to guess what this is? How many people remember playing snakes and ladders? Okay, do you remember how the game works? Is there any strategy in the game whatsoever? No. You roll the dice, and whatever it says, that's how many you move. You land on a ladder, you go up. You land on a snake, you go down. But there's no strategizing to the game. That's why this is a great game to play with, like, 3-year-olds. You don't have to think at all about how the game's going. The dice tell you what to do. So in a game like that, what's the probability that you win it? What is it? Let's say I'm playing you. What's the probability I win? Yeah, it's an even game. Like, it's a complete, based on luck, random game. So the theoretical probability is 1 out of 2, and you could say because there is no strategy to that game, it is completely dependent on the roll of the die. Right? That's it. If you and I were sitting down and playing checkers, oh, that's not a random game. Or chess, that's not a random game. What if we're playing blackjack? 21. It's kind of random, but it's kind of not, because I might have a better sense of the numbers than you. But if we play the same way and we both have the same knowledge of the game, it should be random. It should be a half. And this is where people sometimes ask, so then how do casinos make money? How do casinos make money if they set up a blackjack table, the guy doing the dealing at the table and the experienced player trying to win money both understand the game the same, and it's all about the luck of the cards? Well, there's two things that happen. Number one, the dealer at the table plays a system that will pretty much negate any skill. So it does become a random game, and over time, they have a lot more money than you. So even if you start winning for a while, eventually, if you keep playing, it'll even out and they'll win. The second thing that happens is very often on hands of blackjack and 21, most casinos play that if it's a tie, the house wins. So anytime two hands are tied, you both have 19 or something, house wins. You don't get the money. So there you go. So that's how there's always a way for the house to win when it comes to games of chance. But in a game of snakes and ladders, anybody could win that game, right? It's 50-50. Ooh, shouldn't say 50-50. That's the next lesson. Explain in a sentence the difference between theoretical and experimental probability. Okay, I will say that theoretical probability requires data, I'll say or an experiment to generate outcomes that you can count. Oh, sorry. Oh, I got this backwards. Can you fix that? Sorry, I need more coffee today. Experimental is what I meant to start with that one. Can you fix that? This is why you don't do your notes in pen. Experimental probability requires data or an experiment to generate outcomes that you can count. Theoretical, this is probably two sentences, not one. I'll say in two sentences. There we go. Theoretical probability requires a formula and a situation where the results can be calculated, i.e., they're random. Like, for example, if I wanted the theoretical probability that I was going to beat you at a game of checkers, that'd be kind of hard because it's not a 1 out of 2 chance. Maybe you're a much better checker player than I am. Interesting. What is the theoretical probability that it's going to rain tomorrow? Again, we can't do that. The sky is not like a great big billion-sided die that you roll it, and if it rolls this many ways, it's going to rain. Having said that, they give you a probability that it's going to rain. In fact, I actually looked it up before we started today. There is a 40% chance we're going to see rain tomorrow. Where do they get 40% from? Any ideas? It's an experimental probability, but it's kind of a branch of experimental probability because they don't, obviously they didn't run some weather system experiment in a lab somewhere. But they use data. They use data that can also be historical. What they do is they look up in 150 years of weather records how many days are this time of year with this temperature, with this air pressure, with this cloud cover. They compare the data as best they can, and let's say they found 10 days where it's like, yep, here's 10 days in late May that have similar conditions to the day we're about to have tomorrow. And it rained on 4 of them. 4 out of 10 is 40%. That's how they calculate. They use an experimental probability. Again, some people might call it a historical probability. It's definitely not theoretical. There's no giant die in the sky that somebody's rolling and it's like, oh, turned out a 7, we're going to rain tomorrow. It's not like that. Yep. Can you be a little louder? The time? That's a good question. The question that I'm sure the microphone didn't pick up is, do they calculate what time of day it's going to rain the same way? I doubt it. I have a feeling that would have something to do with when the clouds make it across the sky using their radar trackers. But whether or not it's going to rain just over a 24-hour period is historical probability. So there we go. All right, that is the lesson for the new stuff. I'm going to do one quick reminder of how to do something you should have learned how to do way back in junior high. Do you have a piece of loose leaf handy or something? Let's make a tree diagram. Tree diagrams are fun. It's like, oh, good, I get to draw a tree there. There's my Christmas tree. No, that's not what I mean by a tree diagram. A tree diagram is something like this. Find the probability of flipping, that's supposed to be an F, sorry. Flipping 3 coins and having them all land tails. Ooh, what do you think? Well, I'm going to start by flipping the first coin. So here's my first coin. It's either a head, it's either a squiggle, it's either a head or a tails. Now I'm going to flip my second coin. And that second coin, after the heads, could have been a head or a tail. Or that second coin after the first coin could have been a head or a tail. Do you see where we're going for this? Do you see why they call it a tree diagram? It's like I'm making branches sideways. You could write them up and down too if you want. I just like going sideways because it kind of fits my screen better. And finally, I'm going to flip the third coin. After heads and heads, I could get heads again, or I could get tails. After heads and tails, I could get heads again, or I could hit tails. After tails and heads again, I could get heads, or I could get tails. After tails and tails, I could get heads, or I could get tails. Now, I count the number of final, and I'll say branches, because again, in my head, this is like a tree, right? It's branching sideways. So there is 1, 2, 3, 4, 5, 6, 7, 8. And what's the probability again? Desired over possible. How many possible things could happen? And the answer is 8. How many of them are what I want? Desired over possible. I want all tails. So that is this. Where are my pens? There we go. That is this branch right here. Tails, tails, tails. Notice there's only one like that. So the answer is 1 out of 8. I'll give you a B question. Find the probability of 2 heads and 1 tail. I'll say in any order. So I don't care if it's heads, heads, tails, tails, head, head. Oh, I guess I just counted them all, didn't I? Or I could go back to my diagram and use a different highlighter. I'll use blue this time. And say, where is it 2 heads and a tail? Oh, right here. Heads, tails, heads. So there's 1. Heads, heads, tails. There's 2. And down here, tails, heads, heads. So counting, I get 3 out of 8. And you might be thinking to yourself, you know, I could have just done this by counting all the possibilities. I could have started and gone, okay, I could get heads, heads, heads. Heads, tails, heads. I could get heads, tails, tails. I could get tails, heads, heads. I could get tails, heads, tails. I could get tails, tails, head. 1, 2, 3, 4, 5, 6. Uh-oh. I don't have them all, and I kind of ran out of counting. See the problem with trying to count them? It's really easy to lose track and forget something. What have I missed? Oh, I've missed tails, tails, tails. There's 7, and I know there's 8. What have I missed? I can't even figure it out. Oh, you're right. I haven't done heads, tails yet. Ah, there it is. There's the 8. See how tough that was? And that was only 3 things. What if there was more than 3 things? That's where a tree diagram is really handy. It helps you organize all your possibilities. So you were supposed to learn how to do a tree diagram in grade 8, but I've taught grade 8. Very often we left, just like this course, we'd leave probability to the end, and sometimes you didn't get through it all. So if you didn't see a tree diagram before, you've seen one now. All right, I'll stop there for the day and let you guys do some work. So that'll be it for today's video and lesson. All right, thanks for watching, whoever's watching.